Welcome to day 2 of applications of derivatives. Yesterday you saw how derivatives are tied into motion. If we have a position function, the first derivative is velocity, and then the second derivative would be equal to acceleration. Today we're going to find out that we can use them to tell some properties of curves. But first, a few pieces of notation that's going to be used. So we're all used to seeing the algebraic notation x is greater than 4 to represent an interval or a group of numbers. In our text, you'll see what we call interval notation. Now we're using 4, and we go on to infinity. So this textbook uses brackets. A bracket that points in towards the number means the number is included, and a bracket pointing away from the number, such as this one here, means infinity is not included. We can't be bounded by infinity. We can also use this notation, which we use quite a bit more often in America. We use the parenthesis to emphasize an open-end part of an interval. So we want to say negative 2 is less than x is less than or equal to 7. Our textbook will write it like this, just so you can get used to what you're seeing out of them. We more commonly see this, and this would be acceptable on the IB paper, negative 2 to positive 7 inclusive. You can look on page 634 of your textbook, and there are other examples of the notation used there, but all basically using the two ideas you see above. So on to our application. Now curves on intervals, they increase or they decrease. For example, in the curve you see at the bottom of the screen, from x is 0 to infinity, the function is increasing. But from negative infinity to 0, the function is decreasing, it's falling. We can use our derivatives to find out where this is happening. But first, let's define increasing and decreasing. So we have an interval S on the domain of some function f of x. So we're going to say that it's defined for all x is defined for all s in S. So we say f of x is increasing if and only if f of a is less than f of b for all a and b are members of S. So you take any two members out of S, and if f of a is less than f of b, if that shows that a is less than b, then the function is increasing. So if you pick any two numbers where a is less than b, and f of a is less than f of b, then the function increases in that interval. Right? But that has to be true for every pair that we could possibly pick. And so like even from 1 to 4, we could pick an infinite amount of pairs to have to check through. But that's the criteria for us to be increasing. Decreasing be a very similar statement. It's decreasing if and only if for all A-B pairs that we could possibly pick in S. Their elements or their members of S. So here if I pick an A value that's less than a B value, like if I choose 1, and let me change that. Let me just say I choose negative 1 and negative 4. Well, down here, f of negative 4 is 16, and f of negative 1 is 1, and 16 is greater than 1. So even though negative 4 was less than negative 1, f of negative 4 was greater than f of negative 1. And that would be true for any numbers that I pick on the interval from negative infinity to 0. Now, as soon as I come over into the positive aspect, it no longer works for all pairs. So that's what increasing and decreasing mean, the if and only if. Remember, means we can say if it's decreasing, then this information on this side has to be true. And then we can turn it around and say if this information is true, then this stuff over here has to be true. Mostly used involved in proofs. Another way to look at it is increasing if we're going up as we move to the right, and decreasing as we move to the right if we're going down. Now these two sketches here also talk to us or show us another type of function, a monotonic function. Monotonic functions are always increasing or decreasing for all x in their domain. An example of that one would be f of x equals x cubed. X cubed looks something like this. It's monotonic because it's increasing throughout its domain. F of x equals square root of x would also be monotonic because its graph starts at 0, 0 and increases. So some notation, some terminology. Now, if f of x equals x squared, we can look at the graph and know from 0 to infinity it's increasing. And the same thing for f of x equals negative x squared. From 0 to infinity it's decreasing. Obviously, we're going to deal with functions that are more complicated than these, so how can we use our derivative in order to figure out where it's increasing and where it's decreasing? So let's begin with these two examples here. So the first thing we want to do is we want to find our derivative. So the derivative is 2x. Second thing you want to do is set your derivative equal to 0. So 2x equals 0 means x equals 0. The third thing you want to do is make a sign diagram. And it's going to describe what's happening to the derivative. So for us on this one, 0 is a key point. At 0 we have a value of 0. And that 0 has broken the number line into two intervals, to the right of 0 and to the left of 0. So choose a number to the right of 0, like 3, and do the derivative at 3. Well, the derivative at 3 is 6. That's greater than 0, so our derivative is positive to the right of 0. And to the left of 0, choose a number like maybe negative 2. The derivative at negative 2 is negative 4. That's less than 0, so we're negative. Now our sign diagram here is going to tell us when we're increasing and where we're decreasing. So it turns out that we're going to be increasing anytime the first derivative is greater than 0. So we're increasing when our derivative is bigger than 0, and we're decreasing when the derivative is less than 0. So for this particular function, we're increasing from 0 to infinity, and we're decreasing from negative infinity to 0. If we go through the same steps, the derivative is equal to negative 2x. Set the derivative equal to 0. So we just have a single boundary on our sign diagram. So make our sign diagram. X equals 0 was our value. The derivative equaled 0 there. So these numbers on the top are the signs of the derivative. A number to the left is negative, a number to the right is positive. Excuse me, to the right is positive, to the left is negative. Let me try that again. To the right is negative, to the left is positive. Increasing. This time we're increasing from negative infinity to 0, and we're decreasing from 0 to infinity. Now, sometimes we will have more than one interval. In this graph of this cubic, we can see that at -1 and +1, those are places where it appears that we change from increasing to decreasing. So let's go through our steps here to verify that. Our first derivative is 3x squared minus 3. Set it equal to 0. Go through the process of finding out what value of x is going to cause us to be 0. X is 1 and -1. Now we knew this because of the graph, but if we don't have the graph available, like Newton and Leibniz and thousands of mathematicians after them didn't, they can still find out where it increases and decreases. So our sign diagram for this one, at -1 and at +1, we're equal to 0. Again, this is the sign of our derivative we're putting up above. So we pick a number bigger than 1, like 10. And the first derivative at 10 is going to be 300 take away 3, 297. Definitely a positive value. A number between -1 and 0, -1 and 1. Let's try 0. And that gives us -3. Definitely negative in this region. Now you don't need to write what you're doing as your calculation. Just randomly pick a number. Carry out the arithmetic in your head or with a calculator. Determine positive or negative. So a number on the other side, like f prime of, let's use -10. -10 squared is 100, 300, 297 again. Positive. So this function is positive on two intervals, so it's increasing from -infinity to -1, and also from 1 to infinity, and it's decreasing on the interval from -1 to 1. So things that we need to see as you're working the problems: the derivative, the process of setting it equal to 0, your sign diagram, and then your conclusions that you make based upon the sign diagram. This here, not necessary. I just wanted to show you what I was doing. So let's close by looking at a couple examples. Go through the process again. If you want, you can hit pause, try it yourself, and then start it up and see what I'm doing. See you later if you're doing that, or hang on if you're staying with me. So our derivative is -12x squared plus 30x plus 18. Set it equal to 0. Let's see, we have a common factor of -6. And so now I need to try to factor the inside part. Need to get 5, so let's make that 3, make that negative, so there's negative 5. Plus 1 makes it positive 1 and gives us our negative 5x. So our key values are x is negative 1/2 and x equals 3. Our sign diagram. Negative 1/2, 3. The derivative is 0 at both of those places. A number bigger than 3, number like 5. Now me, I'd put it into this factored part. So I'd have 5 minus 3 is 2, that's positive. 2 times 5 plus 1 is 10, 11, that's positive. So I have a negative 6 times a positive times a positive. And that's going to be a negative. Next, I try a number like 0 is easy. If I put in 0, this whole thing is going to be, let's see, negative 3. And then the middle part's going to be 1, and the last part's negative 6. Those are going to multiply to make a positive. Then a number like negative 5. Negative 5 is going to give me negative 8 in our right factor. It's going to give me negative 15. And I have the negative 6 there. And that's going to end up giving us a negative value out of it. And so with that, we know we are decreasing. On the interval from negative infinity to negative 1/2, and also on the interval from 3 to infinity, and we're increasing on the interval from negative 1/2 to 3. The next one, we'll have to use a quotient rule. Looks like a little bit of chain rule as well. So our derivative is the derivative of the numerator, 4, times the denominator squared, times the denominator, minus the numerator, 4x, times the derivative of the denominator, which is 2, times x minus 1, times the derivative of the inside, 1, all over our denominator squared. So that's going to be x minus 1 to the 4th. Every term has a common factor of x minus 1. So we're going to factor out that common factor. So we're going to have 4 times x minus 1 minus 8x all over x minus 1 cubed. Our numerator, let's see, if we multiply things out, we're going to have 4 minus, or negative 4x minus 4 all over x minus 1 cubed. When does this equal 0? Well, the numerator is negative 4 times x plus 1. We have x minus 1 cubed. Now our derivative is equal to 0 when x equals negative 1. But our derivative in our function is undefined at x equals 1. But it's defined at all other values of x. So as we do our sign diagram now, we need to consider the negative 1 that causes us to have 0 for our derivative, and also have to consider the 1 that makes our derivative undefined. So what we're going to do is have an asymptote in the middle of our graph. So you can't be increasing or decreasing if your function doesn't exist there. So pick a number bigger than 1, a number bigger than 1 like 10, the derivative at 10, is going to be, we go in here, we have negative 44, and down here I'm going to have 9 cubed, which is positive. So it's going to be negative, because I negative 44 divided by a positive. A number like 0, because it's between negative 1 and 1. So that's going to give us negative 4 over negative 1 cubed. So it's going to be a negative divided by negative. It's going to be positive. And let's see, a number smaller than negative 1, like f of negative 10, is going to be a positive 36 over a negative 11 cubed. Well, negative 11 cubed is a negative, and a positive divided by a negative is a negative. So our function increases our function increases Okay, I'm not sure what's happening, but I think maybe the pen has lost its power. So let's finish off of some good old typing. That's going to increase from, who knows what the symbol is, negative is, and let's call this infinity, whatever shows up, to negative 1. And also from 1 to infinity. And again, this is where it's increasing. And then we're going to be decreasing. Let's go back, do a little bit of editing. That's where it's decreasing. And then from negative 1 to 1 is where we're increasing. So I have the pen in now charging, but we're at a good stage because the next one is just what your assignment happens to be. So hopefully you pick up our idea, set the derivative equal to 0 to find the crucial points. Look at each interval to determine if it's positive or negative, and that identifies where we're increasing or decreasing. I'll talk to you again later.